offers a range of services. Check your information panel after dark.
Fuel scooping. System scan complete. Fuel scooping complete.
Hello there, and welcome to the Sleepy Science Channel. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest, your mind slow down, and your thoughts drift. Because tonight, we're exploring the universe itself, not just one galaxy or star, but the vast, expanding whole. We'll move gently from fact to fact, learning about black holes, ancient light, dark matter, and distant galaxies. Some things may surprise you. Others may stay with you, like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you're ready, let's begin. The universe might be older than we thought. Most current estimates place the age of the universe at about 13.8 billion years. This number is based on measurements of the cosmic microwave background and how fast the universe is expanding. But not all methods agree. Some observations of ancient stars and galaxies suggest they may be older than that estimate allows. Others question the assumed rate of expansion or suggest that dark energy may be changing over time. These tensions haven't been resolved, and most astronomers still accept the 13.8 figure. But the questions remain. Could the universe be older? Did we miss something fundamental? It's possible that what we think of as the beginning was just one part of our vast story. There are thousands of rogue planets drifting through space without stars. Not all planets orbit stars. Some are completely unbound, floating alone through the galaxy, without a sun to warm them or light their skies. These rogue planets may have formed normally, then been ejected from their star systems by gravitational chaos. Others might have formed on their own, like failed stars. They're dark, cold, and nearly invisible unless they pass in front of background stars or glow faintly in infrared. Astronomers estimate there may be billions of them in the Milky Way, perhaps even more than the number of stars. Each one is a silent world, adrift in darkness, spinning alone in the vast spaces between. No sunrises, no sunsets, just endless night, broken only by distant starlight. The universe may recycle itself through infinite cycles. The standard model of cosmology describes a universe that began with the Big Bang and will continue expanding, possibly forever. But some theories imagine a different story, one where the universe goes through cycles of expansion and half-lives. In these models, the universe doesn't end with a cold fade or a final crunch. Instead, it resets. After reaching a certain point, it might bounce, collapsing, then rebounding into a new expansion. Each cycle could wipe away the old structures, but preserve subtle traces of what came before. These ideas are speculative, but intriguing. They suggest that the universe may have no true beginning or end, just a rhythm, stretched across unimaginable spans of time. One universe giving rise to another, over and over again. The oldest light we can see comes from 380,000 years after the Big Bang. Before that moment, the universe was a glowing fog, so hot and dense that light couldn't travel far without scattering. But as it expanded and cooled, it reached a turning point. Atoms formed, the fog cleared, and light was suddenly free to move. That ancient light is the cosmic microwave background, and we can still detect it today. It's the oldest direct signal in the universe, not from stars or galaxies, but from the universe itself, when it was just beginning to become transparent. The photons we observe now have been traveling for more than 13 billion years, stretched by the expansion of space into long, cool microwaves. This light is faint, but ever-present, a quiet glow that carries the memory of the universe's earliest clarity. Some stars have planets made almost entirely of diamond. In certain solar systems, the chemistry is very different from ours. If a planet forms with more carbon than oxygen, and the pressures are high enough, something remarkable can happen: a diamond planet. Astronomers have discovered at least one such candidate, a dense world orbiting a pulsar, likely the remnant of a dead star. Based on its mass, density, and composition, the entire planet may be a crystalline form of carbon, essentially, a giant diamond. It's far too hot to sparkle, and it wouldn't look like a jewel up close. But deep beneath the surface, immense carbon lattices could stretch for thousands of kilometers. These strange worlds aren't common, but they remind us how diverse the universe can be. A planet made of rock, a planet made of gas, and sometimes a planet made of crystal. The universe may have no edge, just endless curvature. It's tempting to imagine the universe as something with an edge, a border we could reach if we traveled far enough. But space doesn't seem to work that way. According to general relativity, the shape of space is determined by its contents, and current evidence suggests that the universe is either infinite or so vast and curved that it loops back on itself. If that's true, you could, in theory, travel in a straight line forever and eventually return to where you started, not by hitting a wall, but by wrapping around curved space. This is similar to how traveling around Earth doesn't reveal an edge, just a globe. The universe may work in the same way, on a much grander scale. Not infinite in space, but infinite in journey. The Sun once had a twin, and it may still be out there. Some astronomers believe that our Sun was born with a twin, a companion star formed from the same cloud of gas and dust over 4.5 billion years ago. Many stars form in pairs, and there's no reason to think our Sun was an exception. If it existed, this lost sibling would have drifted away long ago, pulled apart by the slow gravitational tug of the Milky Way. It might still be out there, orbiting the galaxy on a different path, invisible to us now. Some theories even link this twin, nicknamed Nemesis, to mysterious extinction patterns on Earth, though there's no solid evidence for that. Still, the idea lingers that our Sun, steady and alone in our sky, may once have shared its birth with a silent partner, long vanished into the stars. A raindrop of neutron star would weigh more than Mount Everest. Neutron stars are the collapsed cores of massive stars, incredibly dense remnants left behind after supernova explosions. They're only about 20 kilometers wide, but their mass is greater than the Sun's. The matter inside is so densely packed that a single teaspoon of it would weigh billions of tons. If you imagined a single raindrop of neutron star material, it would be heavier than any mountain on Earth. That kind of density defies our everyday experience. Atoms are crushed together so tightly that electrons and protons merge into neutrons, forming a kind of superfluid neutron soup. Neutron stars are extreme objects, small, dark, heavy, and spinning rapidly. But in their quiet mass, they hold the memory of stellar collapse, a final state where matter becomes nearly pure gravity. Light from one galaxy can reach us from multiple directions. Sometimes, light doesn't travel in a straight line. In regions of space where gravity is especially strong, Near massive clusters of galaxies, for example, space-time itself curves. This curvature bends the path of light, like glass bending a beam. It's called gravitational lensing, and one of its strangest effects is that we can sometimes see multiple versions of the same distant galaxy from different angles. These images can appear as arcs, smudges, or even complete rings. They're not duplicates in space, but duplicates in vision, different paths that light has taken through warped space-time to reach our eyes. In a few rare cases, astronomers have observed the same supernova explode more than once, as its light arrived through different gravitational routes. It's a quiet reminder that in the universe, even light can get lost, take a longer path, and still find its way home. The first stars may have burned 1,000,000 times brighter than the sun. The very first stars were unlike anything we see today. Born from the pure hydrogen and helium left after the Big Bang, these stars, called population the third stars, likely formed with no metals at all, making them massive, hot, and short-lived. Some may have been hundreds of times the mass of the sun. They would have burned through their fuel quickly, shining 1,000,000 times brighter than our own star, then collapsing in spectacular explosions after just a few million years. None of these stars survive today, but their brief lives changed the universe. They created the first heavy elements, seeded galaxies with light, and set the stage for everything that followed, including us. Their light is gone now, but their fingerprints remain in the chemistry of ancient gas clouds and in the quiet structure of the early cosmos. Dark matter streams through your body as you sleep. As you lie still, dark matter flows silently around you. It's not some invisible mist. It's a form of matter that doesn't interact with light, doesn't reflect, emit, or absorb it. But it has mass, and it responds to gravity. Our galaxy is surrounded by a vast halo of dark matter, and as Earth moves through this halo, trillions of dark matter particles are thought to pass through every square centimeter of your body each second. They don't collide with your atoms. They don't leave a trace, but they're there, ghost-like, ever-present, and essential. Without dark matter, galaxies wouldn't hold together, cosmic structures wouldn't form, and the universe would be very different. We still don't know what dark matter is made of, but we know this much. It's part of your world, passing through you, silently and continuously, even as you sleep. Some galaxies glow without any stars inside. In the quiet reaches of the universe, astronomers have discovered galaxies that shine, but barely contain any stars. These ghostly systems are full of gas and dark matter, but show little to no evidence of star formation. Some may have lost their stars in violent gravitational encounters. Others may never have made many stars at all. A few are nearly invisible except in certain wavelengths of light, faint smudges in deep surveys of the sky. These galaxies challenge what we thought we knew about how galaxies form and evolve. If they're rich in dark matter, why haven't they built stars? If they had stars once, where did they go? These dim, quiet systems float through space like forgotten bones of cosmic history, reminders that not every galaxy is filled with blazing light. Some simply drift, unseen and unanswered. The universe has a cold spot that shouldn't exist. In the cosmic microwave background, the faint glow left over from the Big Bang, there's a patch of sky that's unusually cold. It's not just a little cooler than its surroundings. It's significantly colder and much larger than scientists expected. This cold spot spans hundreds of millions of light years, and its presence doesn't quite match the smooth randomness we'd expect from early universe physics. Some think it may be the imprint of a vast cosmic void. Others wonder if it could hint at something even stranger, like the collision of our universe with another in the very early moments of inflation. No explanation so far fully fits. The cold spot remains one of the most quietly unsettling puzzles in cosmology. Not a screaming anomaly, but a whisper that something about our universe may not be what it seems. The moon is slowly leaving us behind. Every year, the moon drifts a tiny bit farther away from Earth, about 3.5 centimeters. That's roughly the rate at which your fingernails grow. This slow retreat has been happening since the moon formed, around 4.5 billion years ago. Back then, it was much closer, and a day on Earth was just a few hours long. The cause is tidal friction. As the moon pulls on Earth's oceans, and Earth spins beneath them, a small transfer of energy gradually pushes the moon outward in its orbit. It's a quiet, relentless process, invisible on human timescales, but unmistakable over eons. In the far future, Earth and the moon may become tidally locked, always showing the same face to each other. For now, it just keeps slipping away, little by little, as we spin beneath its distant, glowing light. Binary stars can swap their outer layers like dancers in contact. In some binary star systems, the two stars orbit so closely that their outer layers begin to touch. As they evolve, one star can swell and spill matter onto the other, creating a delicate, spiraling exchange of material. Sometimes the transfer is calm and steady. Other times it triggers bursts of light, rapid rotation, or even a complete merger. The physics is complex, but the image is oddly graceful. Two stars locked in orbit, spinning close enough to brush and blend. One star may end up stripped to a glowing core, while the other becomes swollen and imprisoned. Their fates are bound together. Some of the most unusual objects in the universe, like certain supernova or compact neutron star pairs, begin as these quiet, touching binaries. A reminder that in space, even stars can share, change, and sometimes embrace. The vacuum of space is not truly empty. Even in the deepest, darkest reaches of space, far from any star or galaxy, the universe is never truly empty. According to quantum physics, what we call vacuum is a sea of activity. Tiny particle-antiparticle pairs blink into existence and vanish almost immediately. These quantum fluctuations happen all the time, everywhere, creating a kind of restless background to reality itself. They can influence the motion of particles, affect the behavior of fields, and even contribute to the energy of empty space. This is part of what gives rise to dark energy, the mysterious force accelerating the expansion of the universe. So when we picture deep space as silent and still, that image is only partly true. Beneath the quiet lies a dance of probabilities, a hidden hum of creation and disappearance, always just below the surface of nothing. Time may flow at different rates in different regions of the cosmos. We think of time as steady, a ticking rhythm that flows the same for everyone, everywhere. But in reality, time is deeply linked to gravity, motion, and the shape of space-time itself. In regions where gravity is strong, like near a black hole or a dense galaxy cluster, time slows down relative to places where gravity is weaker. This isn't just theory. It's been confirmed by experiments, satellites, and atomic clocks. But some cosmologists wonder whether time could also vary on even larger scales. Could different parts of the universe experience time at slightly different rates due to how the universe expanded in its early moments? The idea is speculative, but it opens strange possibilities. In a cosmos governed by relativity, even time may not be absolute. It may stretch, slow, or bend, quietly shaped by the space through which it flows. The Milky Way has a hidden halo that's larger than the visible galaxy. When we look at images of the Milky Way, we see a glowing spiral, stars, dust, and gas arranged in beautiful arms. But surrounding this familiar structure is something vast and mostly invisible, the galactic halo. It's a huge sphere of diffuse gas and dark matter that extends far beyond the visible edge of the galaxy, reaching distances many times greater than the span of the disk itself. This halo contains ancient star clusters, stray stars, and vast amounts of unseen mass. It's held together by gravity, shaped by the history of collisions and mergers, and plays a quiet role in the galaxy's stability. Though we can't see it directly, we infer its presence through the motion of stars and the bending of light. The Milky Way, it turns out, is just the bright center of something much larger, a glowing heart wrapped in invisible arms. We've detected light from a galaxy just 200 million years after the Big Bang. The universe is about 13.8 billion years old. But light doesn't travel instantly. It moves through expanding space, stretched and slowed along the way. That's why we can see galaxies not as they are, but as they were long ago. Recently, astronomers using the James Webb Space Telescope identified light from a galaxy that existed just 200 million years after the Big Bang, a blink of time on the cosmic scale. That light has been traveling toward us for more than 13.5 billion years. The galaxy itself is small, faint and primitive, but it holds clues to how the first structures formed. Observing it is like looking through a narrow window into a world we were never meant to see, the universe in its earliest chapters, when darkness was just beginning to give way to stars. The large-scale structure of the universe looks like a neural network. When astronomers map the positions of galaxies across enormous distances, a surprising pattern emerges. Galaxies aren't scattered randomly. Instead, they cluster together along long, thread-like filaments, with vast empty regions, cosmic voids, in between. This interconnected web stretches across billions of light years and is sometimes called the cosmic web. What's eerie is that when you zoom out far enough, this structure looks uncannily like a neural network, the kind found in the human brain. Dense nodes of galaxies are like neurons, and the filaments are like axons connecting them. Of course, the resemblance is purely structural. The universe isn't thinking. But it's still quietly beautiful to consider, the largest structure we know, and the one inside your own mind, shaped by entirely different physics, can end up looking so strangely alike. Stars can sing through the vacuum of space. There's no air in space, so we don't hear sound the way we do on Earth. But stars still make sound, deep, slow vibrations that travel through their interior gases like seismic waves through a planet. These pressure waves make the star pulse and oscillate, and scientists can detect them by observing tiny changes in the star's brightness or surface motion. The field that studies this is called asteroseismology, literally, the seismology of stars. Each star has its own internal frequencies, like a fingerprint, determined by its size, structure, and age. By listening to these stellar vibrations, scientists can peer inside stars and learn what's happening beneath the surface. It's a kind of cosmic echolocation, a way to hear the music of stars across light years, even if the song is silent to human ears. Some stars are older than the galaxies they live in. Galaxies are not built all at once. They form over time, merging with smaller systems and drawing in stars and gas from other regions. That means some stars inside a galaxy can be older than the galaxy's current structure. They may have formed in earlier, smaller galaxies that later merged into a larger one. These ancient stars often live in the outskirts or in globular clusters, tightly bound groups that orbit far from the galaxy's core. Some of them are over 13 billion years old, nearly as old as the universe itself. They carry the chemical signature of a much younger cosmos, when there were fewer heavy elements and only the simplest atoms. These stars are like fossils, quiet survivors from before the galaxy fully came together. Their light is old. Their stories began before much of what we know had even formed. There are galaxies without dark matter, and we don't know why. Dark matter is thought to be the invisible glue holding galaxies together. It explains why stars in the outer regions of galaxies move faster than expected, and why galaxies cluster the way they do. But in the last few years, astronomers have found galaxies that seem to defy this rule, galaxies that behave as if they have no dark matter at all. Their stars move as though only the visible matter is present. This discovery was unexpected, and it doesn't fit easily into current models. Some scientists think the dark matter was stripped away during past collisions. Others wonder if we still don't fully understand what dark matter is. Either way, these strange galaxies suggest that the universe still has secrets, and that the things we think are universal may not be so universal after all. The sun rings like a giant booming bell. Deep inside the sun, sound waves ripple through the plasma, bouncing from one layer to another and setting the entire star into subtle, continuous vibration. These waves aren't like the sounds we hear with our ears. They're pressure waves, low, slow, and far below human hearing. But with sensitive instruments, scientists can detect them and use them to study the sun's internal structure. This field is called heliosysmology. By observing how the sun rings, scientists can map what's happening deep below the surface, its density, rotation, and even its hidden flows of hot gas. The sun, in this sense, acts like a musical instrument, vast, complex, and always playing. We just need the right tools to listen. And what we hear helps us understand not only the sun itself, but stars everywhere. Galaxies follow filaments made of something we cannot see. The universe's largest structures aren't made of stars or gas. They're shaped by something invisible, dark matter. Over billions of years, this dark matter formed enormous filaments stretching across space, and galaxies tend to form and move along these filaments like beads on a string. We can't see the filaments directly, but we can infer them by observing how galaxies cluster and how light bends as it passes through these regions. The filaments can span hundreds of millions of light years and connect vast clusters of galaxies. In between lie great voids, nearly empty regions, where very little matter exists. The dark matter filaments act like a hidden scaffolding for the visible universe, shaping how galaxies grow and where they go. And yet, we still don't know what dark matter is. The structure is there, immense, unseen, and quietly holding the universe together. Space can stretch faster than the speed of light. In normal circumstances, nothing can move faster than light. But space itself isn't bound by that rule. During the early moments after the Big Bang, space expanded so rapidly that regions of the universe were pulled apart faster than light could travel between them. This wasn't motion through space, it was the expansion of space itself. Even today, distant galaxies aren't racing away because they're moving quickly through space. They're receding because the space between us and them is stretching. And if they're far enough away, that stretching makes them recede faster than light, which is why we'll never see them again. It's not a violation of physics, but a quiet consequence of how space behaves on cosmic scales. The universe doesn't need to rush. It simply expands, calmly and relentlessly, beyond what we can follow. Our solar system moves through space like a helical spiral. It's easy to picture the planets orbiting the sun in neat, flat circles. But zoom out further, and something stranger emerges. The Sun itself is moving, orbiting the center of the Milky Way at nearly 1 million kilometers per hour. As it moves, the planets follow in tow, not just circling the Sun, but spiraling through space behind it. The combined motion creates a helical pattern, like a corkscrew or a twisting ribbon. Everything is in motion: the planets, the Sun, the stars, the galaxy itself. There is no stillness in space, only graceful, ceaseless drift. Even as we sleep, we're tracing slow spirals through a galaxy in motion, wrapped in layers of orbits within orbits, a dance so vast we never feel it. Even nothing has a temperature. If you travel far enough from stars, planets, and galaxies into deep intergalactic space, you'll find yourself surrounded by what seems like pure emptiness. But even the vacuum has a temperature. That temperature is about 2.7 Kelvin, just a few degrees above absolute zero. It comes from the cosmic microwave background, the leftover glow from the Big Bang, now stretched and cooled by billions of years of cosmic expansion. This faint radiation fills the entire universe. No matter where you go, it's there. It's the quiet thermal signature of the early universe, still lingering, still measurable. And in the future, it will cool even further. In a few trillion years, the universe may approach absolute zero, but never quite reach it. Because even in the vastest emptiness, the echo of heat remains. Quantum fluctuations may have shaped the entire universe. At the smallest scales of reality, far smaller than atoms, the universe behaves unpredictably. Tiny, random fluctuations in energy can appear and vanish in an instant, due to the uncertainty built into quantum physics. And according to many cosmologists, those brief, random blips may have been magnified during the universe's first moments through a process called inflation. As space expanded at unimaginable speed, tiny fluctuations were stretched to cosmic proportions. Those fluctuations became the seeds of structure, the places where matter would clump, where galaxies would form, where stars would eventually ignite. In other words, the grand structure of the cosmos, the galaxies, the filaments, the voids, may all trace back to fleeting, random events at the smallest possible scale. Everything we see today, born from the trembling of nothing. Dying stars can pulse like heartbeats across millions of years. Not all stars end with a bang. Some fade more slowly, and during their final stages they can pulsate, swelling and shrinking in rhythmic cycles. These stars, called variable stars, change in brightness over time. In some cases, the changes are steady and regular, repeating like a slow heartbeat. The pulses are caused by changes in the star's outer layers, gases expanding and cooling, then collapsing and heating up again. Some stars pulse every few days. Others take months or even years to complete a cycle. These rhythmic stars have been used to measure distances in space, since their pulsation patterns relate to their true brightness. They also serve as quiet reminders that even in death, stars can keep time, not with a clock, but with a long, slow breath across cosmic ages. Earth is inside a giant bubble of hot gas. If you could see far into the invisible wavelengths of light, past what your eyes can detect, you'd find that our solar system sits inside a vast, glowing bubble of hot gas. It's called the local bubble, and it stretches for hundreds of light years in every direction. This bubble is thought to have been carved out by ancient supernova, exploding stars that blasted shockwaves into the surrounding gas, heating and clearing it out. Now our solar system drifts quietly through this low-density region, surrounded by a shell of hotter gas and dust. It's not dangerous. It's not something we can feel. But it's there, a kind of quiet chamber around us, born from violence long ago, now part of the gentle backdrop of our galactic neighborhood. There's a vast, empty region behind the Great Attractor.
Frameshift drive charged.
The Great Attractor is a mysterious gravitational anomaly, a region of space so massive that entire galaxy clusters, including our own Milky Way, are slowly drifting toward it. But behind this immense concentration of matter lies something even stranger. A region known as the dipole repeller, where space appears unusually empty. It's not just a patch with fewer galaxies. It's a vast cosmic void stretching for hundreds of millions of light years. And oddly enough, its emptiness seems to push galaxies away. Together, the Great Attractor and the dipole repeller create a quiet gravitational tug-of-war that helps shape the motion of our local universe. We're drawn forward by unseen mass and pushed back by the emptiness beyond. It's a reminder that in the cosmos, both presence and absence can shape the path we follow. Neutrinos pass silently through the Earth and through you. Right now, trillions of particles called neutrinos are passing through your body, and you'll never feel them. Neutrinos are incredibly light, neutral particles produced in enormous numbers by the Sun, exploding stars, and even the early universe itself. They barely interact with normal matter. They can fly straight through a planet or your entire body without leaving a trace. Some pass through detectors buried deep underground, where rare collisions help us study them. But most simply pass through, unnoticed. These particles are everywhere, all the time, silently streaming through space and matter alike. They move at nearly the speed of light, and yet they almost never touch anything. The universe is full of motion, even when everything feels still. The most massive stars can collapse directly into black holes without a panic. We often imagine the death of a massive star as a violent supernova, a brilliant explosion lighting up the galaxy. But for the most massive stars, the end can be strangely quiet. Some stars are so heavy that when they run out of fuel, their cores collapse inward, and gravity wins so completely, so suddenly, that even the outer layers fall straight in. No explosion, no bright farewell, just a sudden disappearance. This process is called a direct collapse. In a moment, a star is gone, replaced by a black hole, silent, invisible, and crushingly dense. Astronomers have even observed stars that seem to vanish without a trace, as if the light simply blinked out. It's a reminder that not all cosmic endings are fireworks. Some are whispers into the dark. Galaxies can orbit one another like moons around planets. We tend to think of galaxies as isolated islands in space, but many live in small groups where they interact and even orbit one another. Our own Milky Way, for example, has dozens of smaller satellite galaxies. The large and small Magellanic Clouds are the most famous. These companions move around the Milky Way like moons around a planet, slowly tracing long elliptical paths through space. Sometimes, larger galaxies pull stars from their companions, forming streams and tidal tails that stretch across millions of light years. Over time, a smaller galaxy may be absorbed completely. These cosmic dances happen over billions of years, slow, graceful interactions on a scale we can barely imagine. In the quiet of deep space, even galaxies can keep each other company. The universe's brightest explosions come from collapsing magnetic stars. There's a rare kind of explosion called a magnetar hypernova, and it may be one of the brightest things the universe can produce. A magnetar is a neutron star with an unimaginably strong magnetic field, trillions of times stronger than Earth's. If a massive star collapses into a magnetar and releases its energy quickly, it can produce a burst of light and energy far more powerful than a typical supernova. These events may be responsible for some long-duration gamma-ray bursts, flashes of high-energy light that travel across the universe and briefly outshine entire galaxies. The explosion lasts only seconds, but its light can reach us from billions of light years away. It's one of the universe's most intense phenomena, created by a small, dense object wrapped in magnetic fire, collapsing in on itself. The edge of the observable universe is not the edge of the universe. When we look out into space, there's a limit to how far we can see, about 46 billion light-years in any direction. That's the edge of the observable universe. It's not a wall or a boundary, just the furthest distance light has had time to reach us since the Big Bang, given the expansion of space. Beyond that, the universe likely continues. We just can't see it yet. And because the expansion of space is accelerating, some parts of the universe are moving away from us faster than light. That means their light will never reach us, not even in infinite time. The observable universe is like a bubble of vision, not the full size of reality, but just the part available to us. Beyond that, more galaxies, more stars, maybe forever. Some galaxies shoot jets of plasma for millions of light years. At the heart of many galaxies lies a supermassive black hole. And sometimes, as matter falls toward it, not all of that matter disappears. Some of it gets caught in magnetic fields and blasted outward in narrow, powerful jets, streams of plasma moving near the speed of light. These jets can stretch far beyond the host galaxy itself, reaching lengths of millions of light years. We see them glowing in radio wavelengths, forming enormous lobes that mark their reach. Galaxies like these are called radio galaxies, and their jets are among the largest structures in the universe. It's a strange irony. The most powerful outflows can come from the regions around black holes, where light can barely escape. Even silence, it seems, can leave a mark. There's a star that orbits the Milky Way backward. Most stars in the Milky Way orbit in the same general direction, following the galaxy's rotation. But not all of them. There's at least one known star, named Hey 04375439, that moves in the opposite direction. Its orbit is retrograde, cutting against the flow like a salmon swimming upstream. How did it get that way? One possibility is that it was part of a smaller galaxy that merged with the Milky Way long ago, and its orbit reflects that older, different system. Or it may have been flung into its current path by a gravitational slingshot, perhaps involving a black hole or dense star cluster. Either way, it's a quiet reminder that not all stars follow the rules, and even in the vast clockwork of the galaxy, there are wanderers going their own way. The center of the galaxy smells like raspberries and rum. It sounds like a joke, but it's real. Astronomers studying the chemical composition of a dust cloud near the center of the Milky Way discovered a molecule called ethyl formate. On Earth, it's associated with the flavor of raspberries and the scent of rum. Of course, the galactic center doesn't actually smell. The vacuum of space wouldn't carry scent the way air does. But the presence of these molecules hints at the complex organic chemistry unfolding in deep space. There are alcohols, sugars, and even amino acid precursors in interstellar clouds. It's not life, but it's the kind of chemistry life might need. So while space may not smell like fruit and liquor, it contains the building blocks, floating silently between the stars. One galaxy is headed straight for the Milky Way, and it's already touching. The Andromeda Galaxy is our nearest large galactic neighbor, and it's on a slow-motion collision course with the Milky Way. Right now, it's about 2.5 million light-years away, but that gap is closing. In about 4 billion years, the two galaxies will begin to merge. And interestingly, the outer halos of both galaxies Their vast clouds of hot gas and dark matter are already overlapping. So in a sense, they've begun touching already. The eventual merger will be more of a graceful blending than a crash. Stars will mostly pass by one another without colliding. Over time, the two spirals will become one larger elliptical galaxy. We sometimes call this future system Milky Way. It's a long wait, but it's already in motion. A cosmic meeting playing out over billions of years. The cosmic microwave background still glows all around you. Every part of the universe, including the space around you right now, is filled with a faint glow called the cosmic microwave background. It's the afterglow of the Big Bang, light released when the universe was about 380,000 years old. Back then, the cosmos was a hot, dense plasma. When it cooled enough for atoms to form, light was finally free to travel. That light has been moving ever since, stretched into microwaves by the expansion of space. Today, we detect it as a nearly uniform glow in all directions. It's not something you can see or feel, but sensitive instruments can pick it up as a kind of cosmic whisper. This glow is the oldest light we can observe, a quiet signal from the universe's childhood, still echoing through space and time. Some supernovae are powered by invisible collapse, not light. Supernovae are known for their brightness, massive explosions that briefly outshine entire galaxies. But not all supernovae are luminous. Some are what astronomers call failed supernovae. In these cases, a massive star's core collapses, forming a black hole, but the outer layers don't explode outward in a visible flash. Instead, they may fall inward, feeding the black hole silently. In rare instances, we've watched stars that seemed stable suddenly vanish from view. No explosion, no fading glow, just darkness. These disappearances suggest a collapse so complete that almost all of the energy is swallowed. There's still tremendous violence, but most of it is hidden. It's a reminder that not all cosmic deaths make noise. Some happen in silence, deep inside gravity's grip. There are entire galaxies made mostly of gas and dark matter. We often picture galaxies as bright spirals or glowing ellipticals, filled with billions of stars. But some galaxies are barely visible at all. These dim systems contain very few stars, but they still have mass, mostly in the form of gas and dark matter. They're difficult to detect with regular telescopes and often appear only as faint smudges or through indirect measurements. Some of these galaxies may be failed systems, structures that never formed many stars, perhaps because they were stripped of gas or heated too early in cosmic history. Others may be temporary phases in galactic evolution. What they all have in common is subtlety. No fireworks, no spiraling arms, just quiet gravitational presence. They remind us that not all galaxies shine. Some simply exist. Black holes can collide and merge in cosmic dances. When two black holes orbit one another, they emit ripples in space-time called gravitational waves. As energy leaks away, the black holes spiral inward until they merge in a final dramatic moment, two invisible giants becoming one. These collisions don't make light, but they send out bursts of gravitational waves that we can now detect on Earth. The first of these signals was observed in 2015, confirming a century-old prediction by Einstein. Since then, we've detected dozens more. Each one tells a story about massive objects colliding in distant galaxies long ago. These black hole mergers happen quietly, invisibly, but with incredible force, converting entire solar masses of energy into waves that ripple across the universe. And for a moment, the fabric of space itself sings. Some stars die in slow motion taking billions of years to fade. Not every star ends in a sudden explosion. Smaller stars, like our Sun, die much more slowly. After burning through their hydrogen fuel, they expand into red giants, shedding their outer layers into space. What remains is a dense, hot core, a white dwarf. This remnant no longer produces energy. It simply radiates away its leftover heat, very, very slowly. A white dwarf can take billions of years to cool, gradually dimming until it becomes invisible, a black dwarf. But the universe isn't old enough for that to have happened yet. Every white dwarf that's ever formed is still glowing, somewhere, quietly fading in the dark. The death of these stars is less like a firework and more like an ember, cooling gently over cosmic time. Time near a black hole slows down compared to Earth. In Einstein's theory of general relativity, gravity doesn't just pull on matter, it bends space and time. The stronger the gravitational field, the slower time flows relative to areas of weaker gravity. Near a black hole where gravity is extreme, this effect becomes dramatic. If you were to orbit just outside the event horizon, time for you would pass much more slowly than for someone far away. Minutes near the black hole could mean years elsewhere. This isn't science fiction. It's a real, measured effect called gravitational time dilation. We've even observed it in milder form with GPS satellites. Around black holes, it becomes profound. In a way, they don't just trap light, they stretch time itself. The void between galaxies is colder than any lab on Earth. Far from stars, planets, or even gas clouds, the vast spaces between galaxies are astonishingly cold. The temperature there drops to just a few degrees above absolute zero, about 2.7 Kelvin. That's colder than any natural place on Earth, and colder than most environments we can create, even in advanced laboratories. This chill comes from the near-total absence of particles and energy. There's nothing to hold heat, just a scattering of stray atoms and the faint microwave glow of the early universe. These intergalactic voids are the quietest, loneliest places we know. Enormous and empty, stretched across millions of light years. They are the universe's deepest shadows, holding only the background whisper of creation. The universe is getting more transparent as it ages. In the early universe, light couldn't travel freely. The cosmos was filled with a hot plasma, a fog of free electrons and atomic nuclei that scattered photons constantly. But as the universe expanded and cooled, it reached a point where electrons combined with nuclei to form neutral atoms. Suddenly, light could move unhindered. This event, called recombination, happened about 380,000 years after the Big Bang, and it released the cosmic microwave background we still detect today. Since then, the universe has continued to grow more transparent. The formation of galaxies and stars added new pockets of light, and as matter spreads out, there's less and less to block a photon's path. With time, the darkness has become clearer. Space, once glowing and opaque, now lets light pass through almost unimpeded. We've captured the shadow of a black hole. In 2019, the Event Horizon Telescope released the first direct image of a black hole, or rather, of its shadow. The black hole itself can't be seen, but the glowing ring of hot gas swirling around it reveals its presence. This particular black hole lives in the center of the galaxy M87, about 53 million light-years away. The image shows a circular silhouette, the region from which no light escapes, surrounded by a halo of radiation twisted by gravity. It took years of global collaboration, coordinating telescopes around the world to act as a single planet-sized lens. The result was more than a picture. It was a quiet triumph of science, giving us our first glimpse at one of the most mysterious objects in the universe, not through fiction or theory, but through light. You can see a galaxy with your naked eye from your backyard. Most galaxies are so far away that even powerful telescopes reveal only faint smudges. But there's one you can see without any equipment at all, the Andromeda Galaxy. On clear, dark nights in the northern hemisphere, it appears as a soft, hazy oval in the sky, just visible to the eye. It's over 2.5 million light-years away, meaning the light you see began its journey long before humans evolved. Andromeda contains 1 trillion stars, more than double the Milky Way, and it's slowly moving toward us. It's hard to grasp, but you can look up and see an entire galaxy with no telescope, no filter, just the sky, your eyes, and the soft glow of something vast and ancient drifting in the dark. One tiny satellite detected the whisper of a distant black hole collision. In 2015, a small satellite named LIGO detected something extraordinary, a faint ripple in space-time from more than 1 billion light-years away. It was caused by 2 black holes colliding, sending gravitational waves across the cosmos. These waves are incredibly subtle. When they reach Earth, they stretch and squeeze space by less than the width of a proton. Yet with delicate instruments, we can detect them. LIGO and its sister observatories act like cosmic ears, listening to the universe's deepest rumblings. What they heard was confirmation of a prediction Einstein made a century earlier, that even in the silence of space, massive events can send out waves we can feel. A single chirp from the merger of invisible giants, caught by a tiny detector on a quiet corner of a small blue planet. Some regions of the universe are expanding away from us forever. The universe is expanding, and that expansion is accelerating. As space stretches faster and faster, some galaxies are being pushed away so rapidly that their light will never reach us. Even if we waited forever, the space between us and those galaxies would grow too quickly for the light to close the gap. They've already passed a point of no return, slipping beyond the cosmic event horizon. Eventually, more and more of the universe will fade from view. Not because it's gone, but because its light can no longer reach us. This isn't something we'll feel day to day, but over billions of years, it means the visible universe will shrink. The cosmos isn't just growing, it's also quietly letting go. Some black holes may be primordial, born before stars. Most black holes form from the collapse of massive stars. But there's another possibility. Black holes that formed in the earliest moments of the universe, before stars even existed. These are called primordial black holes. They may have formed from tiny fluctuations in the dense, hot conditions just after the Big Bang, regions where gravity pulled matter together into ultra-compact knots. Some of these black holes could be incredibly small. Others might have grown over time. We've never directly detected one, but if they exist, they could help explain dark matter, seed the formation of galaxies, or unlock new insights into the early universe. They'd be older than stars, older than galaxies, silent fossils of the first seconds after time began. Entangled particles may link distant corners of the cosmos. Quantum entanglement is one of the strangest phenomena in physics. When 2 particles are entangled, their properties remain linked, no matter how far apart they are. Change one, and the other changes instantly, even across vast distances. It doesn't transmit information faster than light, but it does suggest that reality at the quantum level is deeply interconnected. Some physicists think entanglement could play a role in the fabric of space-time itself, maybe even helping to hold space together. In theory, Particles created in the early universe could still be entangled today, stretched across the expanding cosmos. If so, there may be quiet, invisible threads connecting distant regions, quantum echoes from the dawn of time, still present in the emptiness between galaxies. The vacuum of space has quantum pressure. Even in perfect vacuum, where there are no atoms, no particles, no radiation, there's still energy. Quantum physics tells us that empty space isn't truly empty. Instead, it's filled with tiny, restless fluctuations, particles and antiparticles appearing and disappearing, fields shifting slightly, always moving. This activity creates pressure, known as vacuum energy. On large scales, this pressure may help explain dark energy, the force driving the universe's accelerating expansion. Unlike other kinds of energy, vacuum energy doesn't dilute as space grows. It stays constant, stretching space faster the more there is of it. It's a strange thought, that the more nothing you have, the more something it becomes. The quiet force of empty space may be what drives the cosmos apart. Black holes radiate faint heat over trillions of years. Black holes are famously dark, so dense that nothing, not even light, can escape their gravity. But thanks to physicist Stephen Hawking, we know they aren't completely silent. According to quantum theory, black holes can emit a faint glow called Hawking radiation. It happens at the edge of the event horizon, where virtual particle pairs occasionally result in one particle escaping while the other falls in. The escaping particle becomes real, a tiny bit of energy lost from the black hole. Over incredibly long timescales, this slow leakage can cause the black hole to shrink and eventually evaporate completely. For a black hole the mass of the Sun, that process would take more than 1 trillion years. It's the quietest kind of ending, not an explosion, but a long, slow fade into nothing. The universe contains more plasma than solid matter. When we think of matter, we usually imagine solids, liquids, and gases. But the most common state of matter in the universe is something else entirely: plasma. Plasma is an ionized gas, a cloud of particles where electrons and nuclei move freely. It's found in stars, in the solar wind, in interstellar space, and even in the vast regions between galaxies. Most of the visible matter in the universe is in this state. Plasma behaves differently from other forms of matter. It responds to magnetic fields, flows like fluid, and can carry electrical currents across enormous distances. On Earth, we rarely see it outside of lightning, fire, or neon lights. But in space, plasma is everywhere, glowing, flowing, and shaping much of what we see, even when we don't realize it. Gravitational waves travel at the speed of light. Gravity doesn't just pull, it can ripple. When massive objects like black holes or neutron stars collide, they send waves through the fabric of space-time itself. These gravitational waves stretch and squeeze space as they pass, moving outward in all directions. And they travel at the speed of light, the fastest possible speed in the universe. It took decades to develop instruments sensitive enough to detect them, but now we can listen to these cosmic ripples from Earth. Each wave carries information about distant cataclysms, how much mass was involved, how fast the object spun, even how warped space became. Gravitational waves are silent to our ears, but they are real, measurable, and surprisingly gentle, tiny shudders in the deep structure of the cosmos. The cosmic web connects galaxies across the universe. If you could map the positions of galaxies on the largest possible scale, you'd find something beautiful. A vast, interconnected pattern of filaments and voids called the cosmic web. Galaxies don't sit alone in space. They gather along invisible threads of dark matter and gas, stretching like tendrils between clusters. Where filaments cross, we find superclusters, enormous knots of galaxies. Between them lie immense, quiet voids, almost empty. The cosmic web isn't something we can see with a telescope all at once, but its structure emerges from large surveys of the sky. It resembles a network, or a foam, or even the branching patterns of neurons. It's the shape of the universe on its grandest scales, not random, but woven, like something grown rather than built. The James Webb Telescope can see galaxies that no longer exist. The James Webb Space Telescope was built to look farther than ever before, and in doing so, it also looks further back in time. Because light takes time to travel, distant galaxies appear to us as they were billions of years ago. Some of the galaxies Webb observes may no longer exist in the form we see them. They may have merged, faded, or changed entirely. But their light is still arriving, a snapshot frozen in time, still crossing space long after the source has changed. This is one of the quiet oddities of astronomy. Telescopes don't show us what's out there now. They show us what was at different moments across the history of the universe. Every deep field image is also a time machine, a gallery of vanished light. Distant galaxies glow with light that left them before Earth formed. When you look at a galaxy a few billion light years away, you're not just seeing distance, you're seeing age. The light from that galaxy began its journey long before Earth existed, before the Sun formed, before our solar system had even begun to take shape. Some of the galaxies we observe today sent out their light over 10 billion years ago. That glow crossed expanding space, stretched and reddened along the way, until it finally reached our telescopes. In a sense, we're watching the universe's ancient past in real time. The stars we see in those galaxies may be long gone. Their light remains, a soft reminder that the night sky holds stories older than Earth itself. Entire galaxies can vanish behind clouds of dust. Even something as massive as a galaxy can be hidden by dust. In some regions of space, thick clouds of interstellar dust obscure the light behind them. This dust isn't like the kind you find on a bookshelf. It's made of tiny grains of carbon and silicates, drifting through cold molecular clouds. When a galaxy lies behind one of these clouds, much of its light can be blocked in visible wavelengths. We only see it when we look with special instruments, in infrared, radio, or X-ray light, which can slip through the dust more easily. Astronomers have discovered entire galaxies this way, lurking behind what once seemed like empty sky. Even in space, appearances can be deceiving. Darkness doesn't always mean absence. Sometimes it just means waiting to be seen in the right light. Some galaxies are surrounded by perfect circles of lensed light. Sometimes the gravity of a galaxy bends the light from something even farther away. If the alignment is just right, this bending creates a phenomenon called an Einstein ring, a perfect circle of distorted light. It's a form of gravitational lensing, where the mass of the foreground galaxy curves space-time, acting like a lens for background light. Einstein rings are rare, but beautiful glowing loops suspended in space, formed not by motion, but by perspective and gravity. The light can come from a distant galaxy, a quasar, or even a supernova. These rings help astronomers measure the mass of galaxies, map dark matter, and study the early universe. They are silent, perfect illusions, natural lenses created by the shape of space itself. The universe may be infinite. When we look up at the stars, it's natural to wonder if there's a boundary somewhere, an edge to everything. But current observations suggest that space might go on forever. We can only see a finite region, the observable universe, but beyond that, the universe may continue without limit. No edge, no center, just more galaxies, more stars, more space. If that's true, it means that most of the universe will always be beyond our reach. We'll never see all of it, no matter how far we look or how long we wait. An infinite universe doesn't mean infinite possibilities, but it does mean endlessness, a quiet vastness that stretches on, gently and without conclusion. Cosmic rays strike Earth from deep space. Every second, high-energy particles called cosmic rays hit our planet, some from the sun, others from distant parts of the galaxy, or even beyond. They're made of protons, atomic nuclei, and other fragments accelerated to incredible speeds by exploding stars, black holes, or mysterious cosmic forces. Most are deflected by Earth's magnetic field or absorbed by the atmosphere, but some reach the surface, and a few even pass through you. These particles are mostly harmless in small doses, but they're a quiet reminder that space is not empty. It's alive with motion, energy, and
Fuel scooping. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Printer page. Frameshift drive charging. 4, 3, 2, 1. Engage. Frameshift drive charging. 4, 3, 2, 1. Engage. Fuel scooping complete. System scan complete. Frameshift drive charging. 4, 3, 2, 1. Engage.
Hello everyone, hope you're all well. Now,
Frameshift drive charging. Ready to engage. Frameshift drive charging. Frameshift drive charging. charging. Frameshift drive charging. Fuel scooping complete. System scan complete. Frameshift drive charging. drive charging. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Frameshift drive charging. Fuel scoping. Fuel scoop disengaged. Frameshift drive charging. System scan complete. Fuel scooping complete. Frameshift drive charging. System scan complete. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Four, three, two, one, engage. Frameshift drive charging. Frameshift drive charging. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Four, three, two, Frameshift drive charging. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. charging. Frameshift drive charging. Fuel scooping. System scan complete. Fuel scooping complete. Frameshift drive charging. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Frameshift drive charging. Ready to engage. Four, three, two, one, engage. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. by 50%. Surface scan complete. Frameshift drive charging. Frameshift drive charging. Fuel scooping complete. System scan complete. Frameshift drive charging. Frameshift drive charging. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Frameshift drive charging. Complete. Frameshift drive charging. Surface scanned by 50%. Surface scan complete. Frameshift drive charging. Frameshift drive charging. Fuel scooping. Fuel scooping complete. Frameshift drive charging. Ready to engage. 4, 3, 2, 1, engage. System scan complete. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Fuel scooping complete. Frameshift drive charging. Fusion drive charging. 4, 3, 2, 1, engage. Frameshift drive charging. Frameshift drive charging. Frameshift drive charging.